So in this last video, I want to introduce kind of one or two other tools or kind of sets of problems that we care about in this P versus NP discussion, because you'll see them pop up if you ever read anything about the subject. So if we want to go about disproving P is being equal to NP, so if we want to prove that P is not equal to NP, there's a really useful subset of problems to consider that really help you make claims about a lot of problems in NP. So really what we need to do in order, like at a very basic level, to prove that P is not equal to NP, all you have to do is show that there is a problem in NP that requires exponential time to solve. So something that's not polynomial time. Now, we know a lot of problems right now that currently only have exponential time algorithms, but that doesn't mean that there's some unknown algorithm that we don't know yet that could solve it faster. And so that's why I say all you have to do is actually a really hard problem, because you have to prove no such algorithm exists. So before we introduce kind of what this set of hard problems is, I need to make one other clarification to the idea of a reduction. So we're going to be using reductions here to make arguments between problems. But what we really need is some way of talking about, is one problem harder than another? And when we're doing these reductions, we want them to be efficient. So we're going to add the qualification about polynomial time reductions, meaning it's just a reduction like we talked about before, reducing problem A to problem B, but that reduction itself needs to be polynomial time, meaning that you can only call the routine for B at most a polynomial number of times, and the extra work that you do to like transform the input or output also needs to be polynomial time. The restriction there being that if you have a polynomial time reduction and you have a polynomial time algorithm to solve problem B, then this whole reduction workflow is now overall polynomial time. Polynomial amount of work to transform the input and the output, and you call a polynomial algorithm a polynomial number of times, say the word polynomial quite a bit, and that end result might be a really large polynomial, but it is polynomial. So if we have this kind of efficient reduction or a polynomial reduction, it now makes us make statements about the efficiency of kind of a lot of different problems. Now, one other thing to take away from this reduction idea of a reduction is it actually tells us a little bit about the hardness of problems. So if you're able to reduce A to B, then in some sense, A should be easier than B, right? Like if you're able to solve B, you could totally solve A by using this reduction. And so we usually kind of use this as kind of an informal or intuitive way of talking about one problem being harder than another. And again, this notion of harder and easier is not quite concrete, but really saying that B is in some sense more general because it's able to also solve A. And so in some sense that B problem seems harder to solve because it's a more general problem. And you'll commonly see this notation A less than or equal to B with the subscript P to say that it's reducible in polynomial time. And that arrow goes in that direction to say that like A is easier than B, or at least as easy. So that's kind of our idea of reductions, just the same idea with just some modification on how we interpret it, and that needs to be efficient. So there is a new interesting set of problems that we call NP-complete problems. So if we want to go about proving that P is not equal to NP, I mentioned that we need to prove that there's no efficient algorithm for some problem in NP. So probably a good candidate to start our analysis with is probably the hardest problem in NP, the problem that's harder than any other problem. So what is this hardest problem? It turns out there's actually not one of them, there's many of them. And we call these the NP-complete problems. So the set NP-complete is the set of problems B, such that B is in NP, so it's any problem in NP, that also is able to be reduced to from all other problems in NP. So a problem B is NP-complete if it's in NP, and every other problem in NP reduces to B, meaning that this problem, any problem in NP-complete, is at least as hard as all of the problems in NP, but it's also verifiable in polynomial time because it's in NP. So this set of problems NP-complete is the set of the hardest problems also in NP, because there are lots of problems in NP, including all of our P friends, right? all the P problems are in NP, but those don't seem particularly hard because we have polynomial time algorithms for. But this NP-complete section of NP is the really hard problems, the ones that are harder than all the other problems then. So why NP-complete? Well, because I mentioned it seems like the right place to start for proving that they're not equivalent. It turns out it's also the right place to start if you want to prove that they are equivalent. Because these problems are the hardest problems in NP, if you find an efficient solution to one of them, you find an efficient solution to all of them. Because you could turn any problem in NP into that problem that you have an efficient algorithm for using a polynomial time reduction. I mentioned, if everything is polynomials all the way down, then the whole total runtime will be polynomial. So that's in some sense why proving P is not equal to NP should be an easy task. You just pick one of these NP-complete problems and prove that it's harder than a polynomial task. Or if you want to prove that they are equal, just pick one of these problems and find one efficient algorithm for it. So far, we've not been able to do either of those. So that's kind of, and I'll, in the kind of next couple steps, I'll give you some examples of what these NP-complete problems look like. But this is why people care about them. They're in some sense the most important problems in NP because they let you answer questions about the whole set. If you find or disprove an algorithm, an efficient algorithm for one of these NP-complete problems, you can kind of make statements about all of NP. I'll show you after this. So, let me give you some examples. These NP-complete problems are weird and usually abstract, and they also weirdly look really similar to a lot of the problems we've seen before. So for example, here are two problems. One I'm calling short path, which is given a directed graph, report if there is a path from S to T of length at most K. That's a problem in P. There's an efficient algorithm for it. And then if you just change that problem a little bit to the long path problem, given a directed graph, report if there's a path from S to T of length at least K, then everything falls apart, and now you have an NP problem. Which means this long path problem is at least as hard as every other problem in NP. It's in some sense the hardest problem in NP. Now, it's not quite fair to say it's the hardest because there's many of them, but it's at least as hard as all others. And even these tiny switches, even though should theoretically not make a big difference in how hard the problem is to solve, really does. There is no efficient algorithm to solve this long path problem that we know of yet, but we haven't proved that it doesn't exist yet. Let's talk about a couple other examples. If we think about the light spanning tree problem, which is like the decision problem version of minimum spanning tree, just asking if there's a tree of weight at most K. That's a problem P. We have an algorithm to solve it. But if you think about the traveling salesperson problem, where what we talked about on Friday, where you need to make this tour around the whole graph with minimum cost, that's suddenly NP complete. And similarly, if we talk about this idea of 2SAT, the satisfiability Boolean formulas, that's in P. And if you just switch that to 3SAT, now it's suddenly NP complete. Now, this is why I said in our first video that if you came up with an efficient algorithm for 3SAT, you've now solved every important problem. That was a little bit of an overstatement. What I meant to say, now that I can say because we have this new terminology, is because 3SAT is NP complete, it's at least as hard as all other problems in NP. And so if you have an efficient algorithm for it, you could reduce any problem to it and then solve those problems efficiently using your new efficient algorithm. So this set of NP-complete problems is really core for having understanding of what is NP, what makes these problems hard. Now, we don't know necessarily why these problems are harder than others, but we know they exist. We know that everything reduces to them. And so you might be wondering, well, how do we go about doing this? Well, in 1971, Cook and Levin proved the first NP-complete problem, which was the SAT problem, not 3SAT, but general formulas with more terms. And then they proved that this thing was NP-complete, that any problem in NP reduces to it. Well, then, a year later, they showed that there is a laundry list of other problems. So they showed a lot of problems computer scientists care about are there. I think the slides might be a little blurry. They might be a little blurry for you. The exact problems aren't necessarily important. There are a lot of them. And they all are very generic. They're usually framed in their mathematical way. rather than the specific applications. But just like how we talked about everything's a graph, well, a lot of these problems that are NP complete are graph problems. So any kind of interesting problem about the real world, a lot of times you run into this NP completeness because it operates on a graph. Now, but wait, there's more. As of 1979, which was, note, a long time ago, there were at least 300 problems proven to be NP complete. Gary and Johnson wrote a textbook where 100 pages of the textbook were just dedicated to listing NP complete problems. Now, no one has made a super comprehensive list since, but there are literally thousands of NP complete problems, ranging from all applications to all levels of importance, and there's new ones added every single year, if not every month. Like, this set of really hard problems is only growing and growing and growing. And if we find an efficient algorithm for any one of them, we have now solved all of them because of this definition of NP complete, where any problem in NP complete reduces to it. If now we aren't able to do any proofs showing how you show something's NP complete, but really you just have to. It's actually not too difficult once we have this kind of large set of NP complete problems, because we don't need to really do this proof for every single possible problem. We just need to do it proof for one of the already known NP complete problems. Now, one thing I feel like I just have to mention, because you'll see it if you look any of this stuff up. I think it's a little bit confusing terminology and differentiation, but I thought I should mention it because you'll see it, is this one other set of interests that people sometimes talk about called NPhard problems, which is very, very similar in some sense to NP complete problems, with the restriction of being NP removed. So NPhard is the set of problems at least as hard as the hardest problems in NP. That's like the intuitive way of trying to understand what this says. In general, you're just able to reduce any problem in NP to it. But we've removed the restriction that these have to be in NP. So NP complete is really the intersection of NP and NPhard. They're the problems that are efficiently verifiable and are at least as hard as all of the problems in NP. But NPhard contains a lot of other really, really tough problems. And they might be so tough that there's no efficient verification at all. So for example, one example problem that's in NPhard and not NP is chess. If I gave you an n by n chessboard with chess pieces laid out, and I asked you, can player 1 win if they play perfectly from this board? There's no efficient verification for that task. So it's a problem that's harder than all the problems in NP, and also is not in NP because there's no efficient verification. There's also a lot of other really scary problems out there. This is kind of the space where there be dragons is marked on the map. There are problems out there that we know have no solution. So not just a solution that's inefficient, but ones that we can't solve at all. So for example, if you were asking on project 2, is my code stuck in a while loop? Or is it just taking a long time to run? That's a problem that has no solution. We have proven that there is no way to write a program to determine if your program will halt. And that problem is kind of one of the hardest problems since there is absolutely no solution to it. There's no way to solve it. And so you sometimes see that as listed as NPhard. That's called the halting problem. It's really interesting, but we're not going to dive too much into it. Now, the reason I wanted to bring up this other set, NPhard, is because whenever you look at these pictures of what does this complexity world look like, they usually include it. So if we're in this worldview where P is not equal to NP, then we have our favorite set P over here, all these efficiently solved problems. And then outside of it, we have NP, all the problems that we can verify efficiently. And then we have these problems NPhard, which are the really hard problems. Some of them might be in NP. The intersection of NP and NPhard is NP complete, the hardest problems in NP. And NPhard is all these problems that are harder than all the problems in NP, including this chess and this halting problem. Now, if we found that P is equal to NP, and remember, the way we do this is you just pick one NP complete problem and you find an efficient algorithm for it. If you're able to do this, everything starts collapsing. NP complete basically disappears. There's no notion of that necessarily. this entire set of P and NP really just becomes P. Because if they're equal, there's no need to have two different sets. Now, there are some problems, even if P is equal to NP, that we still won't know how to solve efficiently. Namely, that halting problem we'll never have a solution to, no matter how many times we try. And that n by n chess thing is still going to be pretty hard. It's not an NP. And so this kind of collapsing of difficulty really only matters in this world of NP and NP-complete. If you solve one of them, it just collapses this whole set down. Don't worry, there will still be lots of hard problems out there. But we really do think that the world operates more like this. Now, we haven't proven that, but we think it's really unlikely for P and NP to be the same. But again, that's one of the interesting things. Why haven't we been able to prove this after more than 50 years of trying, and way longer than that? We haven't been able to do this at all, and it's a really tough problem, and something that is really annoying when you think that should be this really fundamental question of computing that we just aren't able to answer at all. Now, I bring up this notion of NP-complete and by extension NP-hard because a lot of problems you're going to run into in life are going to be these NP-complete problems, either explicitly or in disguise. Maybe you're dealing with an NP problem, you don't realize that you could reduce it to an NP-complete problem, or maybe the problem itself is NP-complete and you might realize it. So the last thing I want to mention is, what can we do in practice? If I know I have one of these terrible NP-complete problems that are really important, but we don't have an efficient solution for yet, and have a really good hypothesis that there is not going to be an efficient solution, what should you do? So I have some suggestions. So if you're working on a problem or a domain where your problem is NP-complete, you don't have to give up. There are usually some common strategies people use. So first is, maybe you're working on a special case that we actually understand better than the general NP-complete version of a problem. So for example, while SAT and 3SAT are NP-complete, 2SAT's not. Even though they're very similar problems, just that tiny change in detail makes it efficient. And so maybe you might have something that looks like an NP-complete problem, but really is actually an easier version of it because of some property of the problem you're working on. And kind of the second usually is, even if you have a NP-complete problem, a lot of times, not always, but a lot of times, these problems are only really bad in some kind of worst case. A lot of times they might behave nicely in most cases, or in maybe particularly nice cases, and your instance of the problem might actually be very similar to one of those nice cases. So a very common strategy is to reduce your problem to something like SAT or 3SAT, and then use a pre-written program called a SAT solver to efficiently, or as efficiently as possible, find an answer, and then you can translate that answer back to something you know. This strategy is used all of the time because people spend a lot of time writing as fast as possible SAT solver. Now, you still might, in the worst case, run into this exponential runtime, but the hope is that most of the time you don't. And so you should hopefully be able to get a faster solution if you use one of these pre-written tools. This is used, the last example I can think of that used this was a few years back. We were doing, the United States did a big reorganization of its broadband, or its radio networks, or the communication networks. And they had to do this whole auctioning thing where they kind of bought and redistributed network wavelengths. And they had to run a bunch of these kind of really bad NP-complete problems. And it was a huge work of engineering to actually get a team together to turn this kind of radio wave network problem into a SAT problem, and then try to write an optimized version of a SAT solver to work on that. And they were able to do it, even though it is kind of this worst case exponential search that should take a long time to run. They were actually in a kind of a nice instance where they could go ahead and run it in the SAT solver relatively efficiently. And they got an answer and it went fine and nothing fell apart for the most part. Now, the last kind of strategy is what we talked about on Friday, is there's a lot of research going into, okay, I'm pretty sure P is not equal to NP. So what can we do about this? We can approximate answers. So can I write an efficient algorithm that approximately computes the answer to this problem, which is what we talked about on Friday with the traveling salesperson problem. So that was a lot of information about problems, difficulty, and kind of the state of the world. I don't expect you to walk away with a perfect understanding of what NP means in terms of that formal definition of the non-deterministic polynomial time, or kind of any of this very, very specific nitty-gritty details of how to write the proofs of this stuff. But I hope you walk away with an appreciation of computing more broadly, outside of just programming, but kind of as a area of interest that we care about and that we want to learn more about. And hopefully this gives you some terminology to go out there and hear discussions when people talk about P versus N. If there is a breakthrough down the line, you'll be able to read them and be like, wait, I remember those terms, because they're really important for how we think about moving through our lives, even though we don't talk about them on a day-to-day basis. Is this very fundamental underlying notion of computing that underlies almost everything we use. And hopefully this lecture gives you a bit of the tools and terminology to approach how we think about these things from a computer science standpoint. So that's all I have for our videos for today. Hopefully you've learned something interesting here today. And during class, just like on Friday, we'll have a Q&A session where I'll be in class answering any questions that you might have about this material, or more broadly, any material we can talk about. Wednesday, as a reminder, we do not have any class, is off because of Thanksgiving. So I will see you all the Monday after, hopefully. Hopefully you have a good break, and I'll hopefully see you soon. Bye, everyone.